Welcome back, developers. Welcome to this explainer. I'm your lead dev for today's Silicon Valley-style Cambridge exam hackathon. Think about it. We are going to treat complex AS and A-level mathematics problems, specifically those incredibly high-tariff coordinate geometry questions, exactly like a logical algorithm. Let's call our main past paper prompt the target mainframe. If you actually want to unlock the highest grades, the A stars, you absolutely cannot just memorize a bunch of formulas and hope for the best. You need to write clean, beautifully executable code. Today, we're going to completely break down this target mainframe so you can compile a perfectly optimized score. It's time to hack the system. Here is our command matrix for today. First, the goal, A-star architecture. Second, core coordinate geometry principles. Third, the procedural framework algorithm. Fourth, critical analysis and evaluation. And finally, debugging principal examiner warnings. All right, let's execute.
Section 1. The goal, A-star architecture. We're decoding the pathway to top grades right now. Now, listen to this quote directly from senior examiners. It completely sets the stakes for us. Mastering the equation of a straight line is literally your core code base for reaching that top tier. I know, it might sound like a super basic foundational topic, but trust me, it is the central node. It connects multiple, massive branches of your entire syllabus. If this code base is flawed, if there's even a slight error in your logic here, your entire application just crashes during the exam. We can't have that happen.
So, here is the absolute crucial point. You must view your answer as a process. The journey is graded just as heavily as the final destination. Let me introduce you to two hypothetical coders we constantly see failing in the exam room. First, we have Dev Alex. Now, Alex is excellent at raw data inputs. Alex can calculate numbers at lightning speed, but causes massive memory leaks by completely skipping the analysis and just jumping straight to the final answer. Classic rookie mistake. Then we have Dev Sam. Sam is great at setting up logical loops, but consistently fails strict syntax precision rules. Sloppy notation, missing variables. Neither of them gets the A-star. Why? Because of the method mark strategy. The examiner firewall is looking for systematic processing. They're grading your algorithm line by line, step by step. If you don't show the work, the system rejects you.
Moving right along to Section 2, core coordinate geometry principles. Let's look at the theoretical foundations of our software. Notice how this table perfectly breaks down the specific mental architectures that examiners are actively testing for. They aren't just looking for random numbers scattered on a page. The theoretical foundations of this topic target three completely distinct cognitive domains. First up, knowledge and understanding. This requires you to deploy precise definitions in airtight logical structures. Second, application. This demands that you integrate this specific code base with totally other syllabus areas. And third, analysis. This is where you prioritize deep analytical depth over superficial breadth. You really can't just skim the surface and expect the program to run. Dev Alex and Dev Sam constantly fail light here because they don't understand the underlying architecture of what they're actually coding.
According to the actual principal examiner reports, building your foundation on these three pillars directly correlates to achieving significantly higher marks. Think of this exactly like your pseudocode outline. Before you even start writing out your equations, you need to establish those precise definitions. Then you have to map out the causal relationships. For example, if line A is perpendicular to line B, what exact effect does that have on the gradients? It's a direct cause and effect loop. Finally, top-tier developers always, and I mean always, reference cross-topic connections. Coordinate geometry absolutely does not exist in a vacuum. It integrates heavily with calculus. It integrates with functions. You've got to link those modules together if you want the system to run efficiently.
Section 3. The procedural framework algorithm. This is the actual code algorithm we're going to use. Let's map this out.
Okay, look at this. Here is the exact, standardized sequence you must run every single time you encounter a complex coordinate geometry problem. This is your core loop. Step 1. Deconstruct the prompt and extract the relevant data. Step 2. Select your analytical framework and apply those theoretical principles. Step 3. Execute the analysis. Now, this is exactly where you must show that clear, line-by-line working to secure those method marks we talked about. Step 4. Verify your results. Check them for reasonableness. Don't just blindly accept a massive number if it doesn't fit the physical space of the graph. And Step 5. Present it all in the appropriate mathematical format. If you drop even one of these steps, your code fails to compile. Let's say Dev Alex skips Step 3, no clear working, memory leak, crash. Dev Sam skips Step 5, bad format, syntax error, crash. You have to run the full sequence.
Never, ever forget that presenting your data with these strict conventions is a totally non-negotiable part of the procedural framework. Remember our hypothetical dev Sam? This is exactly where Sam fails the test. Sam runs all the right calculations, gets the right numbers, but uses incredibly sloppy terminology and completely leaves out the annotations. So what happens? The examiner's firewall system rejects the whole thing. You absolutely need proper headings, you need correct academic terminology, appropriate formats, and crystal clear explicit annotations. Every single line of your math must be perfectly formatted syntax if you want to bypass that firewall.
Okay, Section 4, Critical Analysis and Evaluation. Evaluating output. But wait, stop right there. Halt the compile screen. We're about to hit a major logic error mid-argument, and before we push this final patch to secure maximum marks, you need to optimize your system feed. Subscribe to Ace the Exams at the handle @AceTheExams right now, and turn on all notifications for weekly system updates. Got it? System updated? Okay, let's resume compiling and fix this logic error.
Look really closely at this comparison, because this is how we patch the logic error. We're going to deploy the PEAL syntax structure to debug this. PEAL stands for Point, Evidence, Explanation, Link. The left side, the purely descriptive approach, that might secure you a solid B grade. This is Dev Alex's domain, remember? Merely stating facts and doing basic surface-level calculations. But optimizing to the analytical depth on the right is what actually unlocks the A-star. The higher-order assessment objectives demand that you evaluate alternatives, that you compare different approaches, and that you make fully justified recommendations based on your mathematical evidence. You are essentially moving from being a passive calculator to becoming an active system architect. Using that PEAL syntax structure forces you to explain and link your evidence, upgrading your paragraph instantly. Let's really dive into this. Treating an equation like a logical argument means you must always prove why your chosen formula is the absolute correct tool for the job. If you hit a logic error mid-argument, you must debug it by questioning your base assumptions. For instance, have you actually checked if the points mathematically form a straight line, or are you just blindly assuming they do because they look like it on a rough sketch? The truly top-scoring candidates don't just calculate blindly, they justify every single decision with crystal clear mathematical evidence. They use that PEAL structure to build an impenetrable code block.
We are entering Section 5, Debugging Principal Examiner Warnings. This is our system logs analysis. Welcome to the interactive beta testing arena. So, the absolutely crucial point here is to treat these 3 specific warnings as known bugs. You have to actively avoid them in your own code compilation. I want you to run an immersive reader audit with me right now. Let's run Test 1. Imagine a visual 60-second countdown clock ticking down on your screen right now. We're running a trend extraction. Where do students fail most often? Time's up. It's usually one of these 3 massive system crashes. Bug number 1. Students entirely confuse mathematical cause and effect. Bug number 2. They completely forget to check those strict format and presentation syntax rules we covered earlier. And bug number 3, they provide incredibly generic memorized responses instead of actually looking at the data.
Now for Test 2, our code review. We're looking at a sample student text block, and we need to locate where it fails Cambridge system standards. Well, here is a massive examiner alert. Generic, memorized answers simply do not compile in the A-star framework. You must precisely tailor your output to the specific variables of the prompt. The absolute classic mistake in coordinate geometry is solving the equation of a straight line in a complete vacuum, completely failing to link it back to the context of the question. Is it a tangent to a curve? Is it a normal line? Is it a perpendicular bisector? Your logic must map directly and explicitly onto the specific scenario provided. If it doesn't link back, your code fails the review.
All right, team. We are at the end of our deployment. Here is your ultimate cheat sheet, architecture for completely dominating coordinate geometry questions. We've successfully completed our code deployment for today. To ensure your algorithm runs flawlessly under exam pressure, you absolutely must implement the deconstruct, solve, evaluate loop. You have to maintain incredibly strict presentation syntax to appease that examiner firewall, and you must consistently apply the method mark procedural sequence. Make absolutely sure every single line of working is visible, logical, and flawlessly executed.
So, the ultimate question for you developers is this: how exactly will you adapt your own exam strategy to execute this algorithmic framework on your very next past paper? Take this entire architecture and rigorously test your new system protocols. If this hackathon explainer upgraded your exam software today, I need you to subscribe to Ace the Exams at the handle @AceTheExams right now. Smash that notification bell and leave a comment down below with your specific subject and exam level so we can custom build our next major system update specifically for you. Execute the code, clear the mainframe, and I will see you in the next explainer. Keep coding!